Everyone. So this is something I see as some recent work that I did alongside him and Anthony, who are both here, and then Sebastian Defner, who's faculty at UMBC, United States. So it's actually just recently been accepted for publication in EPL, as soon as we get those proofs. But yeah, as Steve said, like I'm kind of treating this quite informally, so just interrupting everyone if you have a question. Right. So where we start is with classical chaos. So you see then where quantum chaos kind of diverges from that. So typically this is captured by the butterfly effect, where you have strong exponential sensitivity of phase-space trajectories to perturbations in the initial conditions. So here's one paradigmatic example. It's like the Lorentz attractor. As I kind of sweep through this one parameter in the system, sigma, we get very different trajectories in phase space. So down the line, you can rapidly lose information about your starting conditions. So we can quantify this exponential sensitivity with the Lyapunov exponent. So here f is some sort of function you make out of your phase-space coordinates, like say a 2-point function, and you perturb one of the position coordinates, say by some epsilon, and you look at how that path diverges as you take the limit of t to infinity epsilon to 0. And this defines the Lyapunov exponent, where you can see that there's an exponential growth in time as given by the log. Classically, we also have integrable systems, so we have many constants of motion for your Hamiltonian, as there are degrees of freedom. So the kind of classic examples of these are these dynamical billiard models. So on the left, we have some integrable system. There's clearly two constants of motion, like it's energy conserving and you've conservation of angular momentum. So adjacent trajectories are going to be quite similar to each other. They're not really going to diverge. You can kind of roll back time and see kind of what your initial conditions are very, very quickly. Whereas on the right, we have the Budimovich stadium, where if you started on two adjacent points, where we're breaking the conservation of angular momentum here, after a few bounces, your trajectories are going to be quite different, and you also have very little idea of what your initial conditions were in the system. Then the question is, what is quantum chaos? So a few problems with quantum mechanics. So the Schrödinger equation is linear, which is normally quite nice for us, but as a result, overlaps between trajectories will remain constant in time due to unitary dynamics. Even then, we still have a loose notion of a trajectory. You can start talking about quantum mechanics in phase space, but still momentum and coordinates cannot be simultaneously defined. So we have a loose notion of a trajectory there. But you can take a semi-classical limit of some quantum systems, like say a kicked quantum rotor, which shows both integral and chaotic behavior depending on the parameters that you pick. And this has a well-defined semi-classical limit, where in the semi-classical limit, it's going to be, again, accordingly, an integrable or chaotic system. So surely something in the quantum dynamics should be indicative of its classical dynamics. And so therefore, we ask, what is the analog of chaotic motion in quantum systems? And so probably the most tried and tested kind of definition of quantum chaos comes from Bodegas, Giannoni, and Schmidt. It's also known as the BGS conjecture, where they, in this original paper, they look at a few like dynamical billiard models, where they have both a quantum and a classical version. And so it was kind of known for a while before then that for an integrable system, your energy eigenvalues are going to look like uncorrelated numbers, like pulling uncorrelated numbers from a distribution. And so if you look at the level spacing statistics of adjacent energy levels in that system, you're going to get this dotted line here, Poissonian distribution. So the energy levels are going to be uncorrelated. Whereas in a chaotic system, the energy levels should have some sort of repulsion. There should be some sort of mixing of them being a chaotic system, which was known for a while, but they made the jump that the level spacing statistics of these chaotic systems are actually those given by Wigner's random matrix ensembles. And so here they apply to a finite billiard, where essentially you just have a square with a disk taken out of the middle of it, chaotic system. You look at the energy level spacings, and you get this GOE ensemble. So the actual ORMT that your model corresponds to will depend on the symmetries in your system, say like time reversal or the like, for GOE. And so this is the BGS conjecture. It's been proved for a bunch of chaotic systems that have a semi-classical limits. And it's conjectured to also hold for quantum systems that have no semi-classical limit. The power of it is that there's very few like non-exotic counterexamples of this. Generally, it appears to be kind of true, but what we would like is some sort of analog of like the dynamical indicator of chaos, like the Lyapunov exponent that we discussed earlier. And so in order to kind of probe that, we need to find some sort of dynamics that will be indicative of quantum chaos. And this is where we come to operator growth. So we're going to pick some test operator for some, say it's just some spin system, spin chain in one dimension. So generally, you can expand your time evolved operator with like a Taylor series around t equals 0. We're going to have repeated applications of your super operator generating your dynamics. So in this case, we're taking the closed dynamics, unitary dynamics, where L, our super operator, is given by the commutator with H. And so all of the information about our time evolved operator should be contained in this set of LVN applied to your original test operator. And so just for some example, we're going to take some tilted field Ising model, which is going to refer to as a chaotic Ising model, and show how this system displays operator growth. So red here is like our test operator that we're just going to say is going to be poly X at site 1. And applying our super operator to it once will spread some of this information onto the next site, because this is a 2-local system. And not just over onto the second site, but it's going to be a linear combination of a few things. And kind of like behind his head, you apply like the super operator again, and this thing's, you can see it's very rapidly going to come out of control. You're very rapidly going to lose kind of information about what your initial operator was. Not going to bother applying it 3 times. Kind of get the point. This is kind of scrambling, this kind of loss of information about your initial state or operator. And then the operator growth, we kind of refer to kind of growth of support of your operator in Hilbert space. So like the later model we're going to look at is a non-local, it's like a k-local model. So when we talk about operator growth, I just want to make the distinction as the growth of support in Hilbert space, not in physical space. But it's kind of helpful. And so
can I ask a question?
Yeah.
So like naively, like even if you had changed that 1.05 to like 1.03, it would have looked very similar. But like the 1.05 was important to make it
maximally chaotic.
Right. So is there a way to actually tell on this level when it's maximally chaotic just by looking at these types of things?
You have to do some sort of work. There's like a nice recent paper by Anatoly Kolnikov where they take this exact model and they take out the 1.05 and 0.5, choose 2 parameters, and they define the quantum geometric tensor for the 2 parameters, and then they start flowing this metric, and where it kind of starts to diverge is kind of the most chaotic parts of the space.
Okay, so I'm looking at like fixed points of this.
Yeah, so they're kind of trying to find where this model is integrable, which there are some very kind of fixed lines for that, where it's kind of you get slow decay of operators, what they call it glassy phases, and where you find these kind of chaotic phases in the phase space of H. This people generally take this one because this is the maximum. You get the biggest Lyapunov exponent.
No, it'll be in my talk this afternoon.
So moving on to set orthox, we have this.
I think your screen is good.
Tell me just happened now, or
No,
just for a second.
it's tapping.
Still showing on the.
Yeah.
Just pop the thing out of your laptop and back in. I just did. Has this ever happened before?
This is new.
Every week a new thing.
Too much chaos.
Oh, with the screen.
Why did you plug it into your lab? Is it the screen or the?
Is it the screen?
Yeah, so it's still reading the TV on my end.
So it's the screen itself.
Yeah.
The screen, or we can turn it off and on.
No, this power is for the computer.
The quantum computer. The quantum computer has stopped working.
There we go.
Everything's still okay on the Zoom end?
Yeah, everything's fine here. Just go back into play.
So autocs. So we have this CT, this nested, this double commutator, where we have two operators W and V, and we choose them in such a way that they have no mutual overlap and support at t equals 0. So they could be two kind of spatially separated parts of your spin chain. And so they should commute at t equals 0, so CT should start at 0. You can expand this out, where this second part, the brackets here, the real part of which is the autoc. So it's an at-a-time order correlation function. And so this, when W and V commute, this thing should start at 1. You can just free move V through, W through the pairal identities. But as W grows in time, it's going to have some mutual overlap with V, and this function, the autoc, should decay. And so the motivation for this is, again, the semi-classical limit. So let's say we take W as our position operator, V as our momentum, plug it into the W commutator, and take the appropriate semi-classical limit. And this thing is that function we talked about earlier. It grows exponentially as e to the 2 lambda LT. So we have some sort of quantum analog of the Lyapunov exponent thanks to the autoc, which is all well and good in closed systems. We get some sort of analog of a Lyapunov exponent that kind of says how quickly our system scrambles. But some problems emerge when we start looking at open systems. So suppose some work by our collaborator Sebastian Defner kind of show that you can write the autoc when you can take a higher average of your operators. It's related to the mutual information between a partition of your system A and B. So the mutual information will trace the behavior of the autoc. And so what happens when we expose some chaotic system, in this case the SYK model, to some sort of decoherence process? What happens is, so in the closed case, blue, we see kind of information scrambling occur. The autoc will decay exponentially and saturate. Whereas when you apply decoherence, no matter the kind of value of the decoherence, the autoc will have the same kind of steady state in the long time limit. And so when exposed to an open channel, neither the autoc or the mutual information can separate the dynamics of information scrambling within a system to information leaking out to the back.
But it depends on the time scale there, right? I mean, like in the early time, they all decay.
You will still get decay. Well, it depends on how big kind of like your decoherence parameter is in the system. If you're talking about like long time dynamics, and it's all going to look the same once there's an open system. And kind of this again is seen in some work by Zhang et al. From Caltech, where they just take the autoc, again, for this is the tilted field Ising model, the maximally chaotic Ising model. Into the autoc, it should be 1 when the things commute, when your operators commute, and then as it grows, it's going to stop being red, and you have this kind of light cone emerging, an information light cone. And for a bunch of different open system channels, so they have pure decoherence, like phase amplitude damping, and some sort of dissipation here in D. But for all the cases, you see this kind of shortening of the light cone in all cases. So they kind of do won't say naive, but in order to account for the autarch leaking information out of the system, they propose just normalizing it. So then, the identity for W, you're just renormalizing it. So this should account for the fact that the norm of your operator is going to shrink in time. But this alone does not recover the same causal cone. The internal dynamics of the system are actually changed by the presence of the bath. So after some time, like the light cone, you do extend it for a little bit further than without the normalization, but in the long time limit, you see that the bath kind of mixes all your information within your system. So you have not just information decay, but internal structuring, restructuring of this information. So the kind of phenomenological picture I kind of want you guys to think of when we talk about the competition between operator growth and local decoherence is this. So again, we go back to the same picture of an operator starting at site 1, but now on each site there's some sort of local decoherence channel I'm calling P here. So as we grow, the time evolved operator is now subject to another local decoherence channel. And as it grows further, it's subject to more and more decoherence. And at some point, these two competing effects, the unitary part that's trying to grow your operator and the decoherence part, are going to kind of cancel out. The decoherence is going to appear so strong, it can't really grow any further.
Fair. So local decoherence was the same decoherence file they were before.
Yeah.
Okay. Does that make sense for a physical system that they be uncorrelated channels?
Physically, you're more like subjected to kind of local decoherence, say, top-down experiments, and it's all on site. Well, in this kind of model, the environment is effectively measuring the size of your operator. The environment kind of knows like how big the operator is. And you can model this through this sort of size measurement superoperator I'm calling S, which just measures the size of the string in your operator O. So we have the unitary part, and then this part where mu is the strength of your decoherence channel that's kind of measuring your operator. And so a recent work by Thomas Schuster and Norman Yao, around in October last year, they kind of applied this kind of intuitive picture to a random unitary circuit with this sort of decoherence channel, local decoherence modeling this way. And they look at the average size of your operator distribution. So the operator distribution is you pick a basis, in their case, the polystring basis for their circuit, and they're looking at what is the kind of average of that distribution in time. So for a random unitary circuit, the actual the mean should grow in time, and then the width of the operator distribution also grows in time. But as you add decoherence, so as these lines get brighter, there's more and more decoherence, you effectively cap off the size of the system at a shorter time. You see that the effect of this local decoherence caps your light cone from going any further. Your circuit's not going to explore its full space. So we do see again that information gets restructured. The operator does not grow to the same extent. The light cone can't be extended all the way out. But we're only here looking at the mean, and it is just some sort of knowledgeable model that they're applying here. Can we probe the internal structure of your system under decoherence more than just the mean string side? Yeah.
So we know that in from monitored quantum circuits, you also see that if you have measurements, it can increase the complexity of the circuit. So here you say, because I mean that's as far as I understand your argument is the environment measures this measures these operators, so you get smaller correlation lengths. Is that an artifact of the specific noise model you choose, or is it a more general statement you want to make?
I wouldn't say this is applicable for all environments. Like as you said, if you're doing these kind of measurement into phase transitions in the surface, it's going to be slightly different. I think this is just more for trying to create some sort of scrambling process, but you know, I've got some sort of noisy local channels in my experimental setup. That's gonna in the long time run really affect my ability to see scrambling in my system. And so
I was just gonna ask, so, if I apply this decoherence to a hard random operator rather than like an initially local operator, presumably like in that case, actually, do you have any intuition for what happens there? Like, what is the size?
I
Does
think
hard random just not care?
I think in this case, we started with like a higher random one that could pretty much support over the entire circuit. You probably will see S bar move down and then increase to a smaller length because basically your decoherence is going to dampen the longer string contributions to the operator faster than the shorter one.
Okay, so you're effectively projecting it into the smaller.
Yeah, so sorry, like the kind of eigenvalue of S applied to O is just going to be the actual string length of O. So the longer strings get dampened quicker than the shorter ones. So it's the competition of how fast can you make long strings versus how fast the long strings dampen.
Maybe we just stop share and reshare. The
Yeah.
slides on the Zoom link went a bit weird.
How's that?
Yeah, it's back to normal.
So as an aside, like returning again to that Taylor expansion of the time evolved operator. As I mentioned, like all the information about your time evolved operator is contained in this set. And in order to do some sort of useful things with this set, it would be nice for this set to be some sort of orthonormal basis or orthonormal subset of Hilbert space for dynamics. So we can do this with the Lanczos algorithm. So we choose some initial operator as before. We regard that as a vector in Hilbert space. So here I'm giving it a click curly cat for this case. Then we just need to equip ourselves with some sort of inner products. So here we're taking some sort of like trace norm of these two operators. Things kind of do get hairy at finite temperature, or like there's kind of an arbitrary choice of inner product. They all give you kind of very inconsistent results, both for this and for autops. But we're going to work at input temperature. So we don't have that ambiguity. So we apply L to O0, and then we have to renormalize it by dividing by the norm of our new operator. And this gives us O1. And then we do it again. We apply L to what we just got, and then we subtract away the kind of support on, or the kind of linear dependence on the previous operator. We get new AN. Now we just need to normalize that AN again with the norm of itself. So it's like a Gram-Schmidt-like process where we're going to end up with a set of these ONs, which we're calling the Krylov vectors, and these BNs, which we're calling the Lanczos coefficients. And so, as I said, we get these things out with the nice kind of orthonormal properties of this Krylov basis. And the other very nice thing is your super operator, L in the spaces, takes on this nice tri-diagonal form. So you have your Lanczos coefficients on the super diagonals there. So this kind of looks like the super operator for a tight binding chain, with the caveat that each site, is actually, in your initial polystring basis, each time you apply L, you're going to be tying together a few operators together as a new kind of Krylov operator, and these are all going to have these are all independent of each other. And so as you go up this kind of Krylov chain,
It's a touch screen.
as you kind of go up the chain, like even though you have only one support on one Krylov space operator, there's like a lot of information, or kind of this Krylov operator captures a lot of non-local support. Say you have like a two local system, ON is going to have like support over n-1 sites. It's going to be a linear combination. So very quickly, your local operator O is going to grow into this bath of Krylov vectors. And so one thing to note is that the Krylov basis is then like the minimal like basis or subset we would describe the dynamics of the operator. So this was the famous operator growth hypothesis. comes into play, where they make an assertion that for chaotic systems, these Lanczos coefficients should grow as fast as they possibly can, with some kind of tight bands not in the case, which indicates that this should be linear with n. And the way it grows is given by this kind of alpha, which they call the growth rate. So in their original paper, they applied it to a few models, and they saw this was the case. So for the SYK model, you see this linear growth in your dn's. For an integrable, I think XXX model, you see this kind of growth of square root of n, and then for a free non-interacting model, it's just of order of 1. And the nice thing about this alpha is it actually upper bounds the alpha of exponent that you will get from your autoc. So in some ways, it's a kind of better dynamical indicator of your scrambling than the autoc. It upper bounds it. And so we're kind of, before this, we were talking about open systems. You can also apply like the Lanczos algorithm in open systems using this bi-Lanczos algorithm. We're going to be involved in the left and right vectors separately, making it bi-orthonormal instead of orthonormal. So here our operator, its time evolution is described by a Lindblad master equation. We get the kind of same thing. We get tridiagonal basis in the end, where we're going to have some sort of imaginary terms along the diagonal, and then terms that differ by a phase in the superdiagonal. So I kind of won't get into the details. There's a bit more involved, but you end up with something that is qualitatively the same as the closed case. We can't define some sort of minimal basis for the dynamics in the open case. What are we doing for time?
25.
And so this is kind of where we define our notion of information scrambling in our paper, the spread complexity. So out of time independent, closed, and Lindblad, like Markovian master equation evolution, we actually can't find this Krylov basis. We can't find the minimal basis for the system. So if you wanted to study scrambling kind of outside of these like paradigms, if you want to look at something more exotic like non-Markovian dynamics, or say you're interested in some dynamics that had no kind of super operator description, what would we do then? So we want to define some sort of grossly supportable operating time in some arbitrary basis, not tie ourselves to the Krylov one. So for our time involved operator xt, we kind of pre-choose some basis bn, and then we build up our operator size distribution, these PBs, in that basis. And then what we do is we just pick the Shannon entropy of it as QI people. That's, any chance to do that, we do. And then to render this as a complexity, we just take the exponential of it. We have kind of one other constraint, is that your initial operator x0 should also just be a single element of your basis, to enforce that you start at complexity 1 at the start. So effectively what this does is it measures like the amount of basis elements that are really contributing to your time evolved operator at any time. So you can see kind of how complex your dynamics are in that basis. And we provided proof in the paper that this spread entropy is minimized by the Krylov basis. So if you want to explore some sort of universal kind of growth of your operator, the Krylov basis will be the one to pick, but you're not tied to it. So you can in principle choose like a poly string basis, or as we will do, like a Majorana string basis for the XYK model, and start working there. And the nice thing about taking the entropy of the distribution is you're kind of getting more information about higher order moments in your distribution. You're not tying yourself to the mean. Like for instance, in some circuits, like autocs have the same behavior. They only start to differ when you look at fluctuations of the autoc. Like you really want to characterize complexity in that way. So by taking the entropy of it, we gain more information than we would otherwise. And so the model we apply this to is this SYK model, the dissipative SYK model, which has kind of just become popular in the field in the last couple of years. Here are kind of degrees of freedom, are these Majorana fermions, which you define by their anti-commutation relation. They're effectively like half a fermion or half a qubit. And the kind of interesting thing about this SYK model, here we take 4 Majorana fermions and make them interact together with an interaction strength J, that is drawn from a Gaussian distribution with zero mean. But it's completely random. It's as well as its Krylov basis for both the closed and the open case, we're going to consider basis of Majorana strings, where we make our basis out of all the strings of length 1, all the strings of length 3, etc. Only the odd string lengths. So as you can see, if you start the string of length 1, you're only ever going to have odd number strings. It's like two kind of parity subspaces almost for the model. So you start with some local string here, you go along the graph where we have this kind of interaction vertex of 4 fermions, 3 are going to come out, and it's going to keep branching off in that way. Yeah, interesting thing about the SYK model is you're very rapidly going to grow into this bath of longer strings with random coefficients as well. So it's going to be it's a very interesting scrambling model to study. Not just for that, but it's like analytically tractable in the thermodynamic limit. It has like these nice self-consistent Green's functions relations, but we don't really make use of that here. We kind of work at finite size. So with our kind of framework, we want to then study operator growth versus decoherence. So the unitary part of the SYK dynamics is like that graph driving us to a linear combination of long odd length Majorana strings. We introduce isotropic decoherence channel to this as a competition to this effect. So here our jump operator is just individual Majorana fermions, and as we crank through in the paper, this has the same effect as that Norman-Yau paper where it dampens the longer strings faster. Like the eigenoperators of the dissipative part of the Lindblad master equation are just the string length operators. The eigenvalues then are just your length. So this is the dissipative part essentially just measures the lengths of your strings. So for say an initial operator that we're choosing as just the first Majorana fermion, as you evolve in time, it's going to be some sort of linear combination of these string operators, and then as I was saying, yeah, the eigenoperators of LD are just your different string lengths. So it dampens strings at a rate proportional to their length. So it's very true to that chronological model that Yau and Schuster are using. And so we first apply this to the n=8 SYK model, and we see very similar results to them. So in the closed case, our complexity grows and then saturates because we do have a finite size system. It's not going to grow indefinitely. But as you increase stronger and stronger dissipation, as we kind of go down the chart, we see this kind of dampening of complexity of a model. We can describe it by less and less basis elements. So yeah, decoherence caps the potential complexity of the operator. So we have a hierarchy of complexity that exists even in the long time limit. So for this same setup, if you were to look at the OTOC or the mutual information, all these lines where mu is not equal to 0 all will be the same at the long time limit. They'll all saturate at a half, as we saw before, but this spread entropy really does probe the internal scrambled dynamics of the system, tell the differences in complexity. So the kind of statement we want to make here is that decoherence, like with this sort of model, it simplifies dynamics. And so if you look at your Krylov space dimension as mu grows, the effect of the channel gets stronger, obviously, and the internal dynamics of the system is less complex. So there's less and less numerically relevant basis elements for your dynamics. And then in the very strong mu limits, you kind of get this kind of xeno blocking. Your operator is just not going to grow off the first side.
Yeah, question. So the dissipative part that you wrote commutes with the fermion parity. Mm-hmm. How important do you think is that you preserve that symmetry in the interaction to have this effect? Because yeah, if this happens, you don't mix these sectors that you analyze independently in SYK, but if it does, you might mix and then something.
Yeah, I think if you had LIs that were, with 2 Majorana fermions would mix these 2 sectors. So again, it'd be also then interesting to have not just a 4-body SYK model, maybe a 3-one as well, kind of have access to the full space instead of in that case. Like, you kind of have the opposite effect when you start with an even string operator at the start. Here we take 5-1. If you take 2, you actually get driven to, it dampens the shorter strings first. You kind of get the inverse of the problem.
But you're saying if you so with the same decoherence.
So when you start with an even string, and you chug through this part, you find that the eigenvalues are not SI, the individual kind of string lengths, they're n minus SI. So they dampen the longer string slower than the short one. It's just kind of a quirk, like we just choose the odd kind of subsector because it's kind of more true to this kind of model. Like in principle, if we were to be kind of even more true, like we would take the tilted field-Ising model and just do, we wouldn't have any of these kind of semantics for weird subsector behavior. I think the model itself is not so important. The kind of that we're able to probe, operator growth versus decoherence and see a kind of hierarchy of complexity is kind of the takeaway. And then with open system effects, like I don't know, your circuit or whatever you're trying to simulate becomes far less complex when you have some sort of dissipation. So we do the same for the string basis that we said before. We have the same hierarchy merging, but much quicker. Because essentially, in the Krylov basis, it looks like a local type binding chain, as we said before. It has this tri-diagonal structure. So it hops from O1 to O2 to O3 in this way. Whereas in the string basis, due to the nature of the SYK model, like you apply L once, you're going to have strings of length 3, then access to strings like 7 of length 9, you're very quickly going to saturate through the basis. So the initial growth is going to be quicker, but you have the same hierarchy emerging. So we do posit, like if you looked at it like a 2-local model, the 2 pitches are going to be a lot more similar. But in general, like the string basis, because it preserves this hierarchy, you see it's kind of stable in the long time limit. It might be a natural basis to pick when the Krylov basis is not accessible. Like ongoing work, we're looking at like non-Markovian collision models, applying it to these sort of systems and seeing not what happens not just when you have operator growth versus decoherence, but operator growth versus decoherence versus information feedback into the system. It's a third kind of parameter to choose.
But so just remind me, then the growth, the initial, because in the Krylov basis, the initial growth corresponds to the Lyapunov exponent, right?
So the initial growth of your complexity should go as e to the 2 alpha t. While
in the string basis, you have a much faster initial growth. Is there any meaning you can associate to that? Like to what that exponent is?
Like I said, I think you couldn't really attribute any universal behavior to it. I think if you want to extract some sort of universal scaling parameter, like first you'd want to be in the thermodynamic limit, and secondly, you'd want some sort of universal basis, like the Krylov basis, something that's minimal. I think it's more of a probe of scrambling dynamics rather than extracting anything universal for it when you pick some sort of arbitrary basis. But in a lot of cases, that's the best you can do. So just for some discussion at the end, like just to recap, operator growth within a system can compete with open system effects. And so our spread complexity provides a framework to probe this phenomenon and really kind of gain information about the internal scrambling dynamics of the system, people with an open system channel. So the Krylov basis is a natural basis to define some sort of universal behavior in this framework, as it's the minimal basis to describe the operator dynamics and minimizes our spread complexity. The string basis has been used to previously study operator growth for the SYK model and in random unitary circuits, as well as like the polystring distributions and its kind of behavior. It's kind of well studied. So while it's not the minimal basis, it can still probe operator growth phenomena, particularly when the Krylov basis can be found. For example, in such circuits or with time-dependent superoperators or non-Markovian superoperators. to us.
Yeah, any last questions?
So I didn't understand what kind of decoherence was. Did you try? Like, do you think this behavior that you see is generic for most kind of noise or decoherence you can put there, or is it somehow?
So I think for any sort of like spoiling with decoherence, or like here we're just using like depolarization, but if you chose just any sort of pure decoherence process, or even nothing with disabled process, it should you should get some hierarchy of complexity emerging. That's how open system effect is strong.
I mean, what we looked at was basically dephasing or depolarizing.
It's driving you to like the center of the block. It's like, yeah, dephasing in all directions.
So I don't know what will happen if you had like a pure dissipative process that's taking you to like, because I mean, if you think about simple amplitude damping, that will take you, it drives you to like a single basis state, basically, right? So in some sense there, it might be a bit weirder, right? So, I mean, I don't know the literature like you do. So has anyone looked at
No.
that's something that's really something like thermalizing again to a finite temperature or some sort of amplitude, like pure amplitude damping?
I mean, I've done the same with just like with that SYK model with the decoherence in the computational basis, which I think the SYK is not a pure decoherence. It's just to copy that paper by Akram last year.
Okay.
And you get the same sort of figures out. But anything kind of more rigorous and just like, yeah, changing few terms in the mathematics.
You had a plot towards the end where you were showing complexity as a function of the decoherence parameter. Yeah, so if you show all of the line, the previous slide. Yeah, so like the v equals 0.1, it almost looks like it's peaking and coming back down. Do you think that's a physical effect?
Yeah, it's probably something like some like the wave function into the momentum on the Krylov chain bounces back from the fifth site to the main node support and forward. Like, it doesn't slow and stop. It kind of,
Okay, I mean, I'm just
Yeah,
curious
yeah,
about like
curious
what
on
would
the-
set the like peak of the complexity. But presumably, like if you cranked up you even higher, you would be able to tell. There maybe it's just too close to the bottom of the plot. But
I think it is something that is going to emerge, right? I mean, I think if the decoherence is really strong,
yeah,
then what it wants to do is do that xeno blocking, wants to keep you on one spot. But like the unitary dynamics will kick you out of that a little bit, right? So if the decoherence effect is really strong, but not like infinitely strong, then the first application will increase. But then like the decoherence kind of kills everything off really quickly.
okay,
That
so
I
it's
think
like quantum xeno, but not in
not
the
quite.
actual limit.
So I think
okay.
while you don't see it in the when the decoherence is too weak, then I think you get a lot of spreading, but then things sort of is sufficiently smoothed out. But if you get into this kind of interesting region where they're kind of almost comparable in strength, it seems like you get a bit of spreading initially kind of dominates the dynamics, and then the decoherence takes over.
Right,
I think that's what
so you
peaking
expect
is.
that as mu gets larger, the x-axis of this peak will move closer and closer to zero.
That's what I think so.
Okay.
But I think it is a physical effect. I think that's meaningful there.
Okay. I also had a more abstract question, which is you mentioned, or you said you proved that when the Krylov basis exists, it maximizes spread complexity. But presumably, even in like the non-Markovian case or the time-dependent case, there should be some basis which maximizes complexity. Do you have any understanding of like what it is in cases where Krylov isn't well defined?
I think maybe the cheeky answer would be like, if you can find it, then that's the Krylov.
Well, yeah, okay, so you think somehow it's gonna be the thing that like lines up with the time dependence in such a way that.
Yeah, I mean, if you can find some sort of like minimal basis that can resolve the dynamics, I think elucidate almost universal behavior. Like, I'm sure you could like just sample the dynamics
Yeah,
of your time evolved operator, make some sort of linear independent set, and then see that it results in dynamics and pull up like squint and say that's the Carolan face.
yeah. I mean, I guess you could also do this even without continuous time evolution, like these quantum cellular automata or whatever. I don't know if that's interesting. I mean, I know for some of the complexity growth results, that's a useful thing to know.
Yeah, well, kind of a caveat, like I'd say nothing about chaos in the second half of it. Like I think dynamics are not a very good indicator of chaos. Like, this is all about scrambling.
Yeah.
The chaotic systems scramble, but not all scrambling systems are chaotic. Like there's a few like very notable counterexamples, like the LMG model, which is fully integrable but has a exponential growth nested or double commutator. If you look at the Krylov complexity for the LMG model as well, you have some sort of exponential growth for that. It gets a bit murky when you start looking at dynamics.
Do you think there's some equivalent? So like, okay, when people talk about state scrambling, right? There's some notion of quantum scars which preserve integrability even when the Hamiltonian is chaotic. Is there like a operator scar notion where there would be like some set of like for a typical operator it would grow, but are there like weird operators that?
I mean, if it commutes with the Hamiltonian, I think trivially.
But that's like not really what's going on for quantum scars. I think it's like there's, I don't know. I would like to understand quantum scars better, but yeah, I think. Well, okay, there's like many body quantum scars which are not quite the same thing as these like chaos theory scars, but somehow I think they don't commute with the full Hamiltonian, but you're in some subsector such that like the projection of the Hamiltonian onto that sector it commutes with.
It's interesting to look at like there be some perturbations like fragment Hilbert space or Bragg ergodicity.
Yeah, I have a fairly basic question. You define the spread complexity by the distribution of strings in your expansion of the operators. When they compare to the initial distribution. This should be related to some sort of entanglement scaling of the. So you take the state and then you take like some cuts and then you change the size of the subsystem and then observe the scaling in the reduced entropy. So is there a quantitative relation? Like say you have a spread complexity of this, does some function of it bound?
It would be nice. Not that I know, but that'd be interesting to look at.
Like for pure states, I think it should be the case. Like for unitary dynamics, this is
the bond dimensions.
Yeah, right. You just write it as an MPO and then cut it and then see how much it has.
Nice test for seeing like, can I do it with only like bond dimension 2 just that close to like the different so the most relevant part.
So this should be related to like the size of the size for dilation or whatever, like how many Krauss operators you need for the
Yeah, that's one way to think.
But so what you would think that if you have like a low spread complexity, then it means that the dynamics or whatever is like easily simulable with like MPOs or something like that, or?
I mean, that would be like the next question I was just interested in, because for me it makes sense to think about entanglement spreading in these systems. So I was curious if there should be a relation, but maybe not.
That's why I kind of wanted to apply to some circuits where I don't think you learn anything new, but something like Clifford dynamics, where you can describe it with just a few maps polystrings to polystrings. The complexity should be low, and like that indicates that they're quite classically realizable.
Yes, I think there's some work on like even monitored fermions where they look at fake like Lindblad master equations, just look like this, like where they have some like weak measurement and some unitary dynamics.
But in general, can you like totally
see a measurement induced phase transition in this parameter describing the strength of this weak measurement?
Can't you totally decouple entanglement velocity from butterfly velocity though?
Yeah, don't know what
Like
these
it.
two terms are.
Growth of entanglement
Yeah.
versus, light cone, and
Mhm.
like, I don't know, I mean, the
Yeah.
models I know are kind of exotic, you have to like put it on like a weird graph, like a tree structure or whatever,
Mhm.
but you can totally like have systems where there can be lots, very fast scrambling without like
Yeah.
any effective growth of entanglement.
Yeah, because the scrambling can have a very preferred basis, right?
Right.
If the scramble is like agnostic enough towards the
Mhm.
local
so
basis, then
generically,
this
I
should
think
be
they should be
yeah.
overrated. Yeah, okay, so
Yeah.
if you like averaged over,
But
Yeah, I mean, I actually wanted to ask something that's related, because I wanted to ask if you had thought about how this relates to the simulability of this dynamics. You say that the
Yeah, I think that's
complexity stays low.
completely applicable, like, for example, with the Clipper, that I want to see like if you introduce Clipper plus T as your set, like, or, see how the complexity changes there in that case.
Yeah, I mean, even in the simple case, so like a circuit case, and you expand things on the Pauli basis, then you can see that this noise can sort of damps out, or
Mhm.
the polarizing noise at least.
you can literally use the Krylov method to simulate stuff, right?
Probably,
There's
yeah,
like,
or you can
packages.
forget the longer Pauli
Yeah.
strings, and then
Mhm.
you can simulate things. But of course, if you do more complicated forms of noise, then it's not less clear what you need to do. But if you say that in general, this reduces the complexity, then maybe it means that there is a way.
Mhm. I mean, yeah, this implied then that somehow open systems that I would think are much harder to simulate or
Easier.
kind of easier. That seems like a very counterintuitive thing to say, right?
the whole like state preparation community would tell you that, right?
Yeah.
Like the whole Gibbs state
Yeah.
people, they're like, oh, you just find a fixed point and then,
Yeah.
but of course, they never actually,
Yeah.
implement their system, they just say it's a super operator.
I think Schuster and have upcoming work on exactly that.
Okay.
Like making some sort of circuits more physically real or numerically realizable by introducing them.
Okay.